Hey there. All right, today we're going to do similar polygons, and we're going to use that proportion stuff that we did yesterday. We're going to use that here, and this is where we're tying in the geometry part of it. So we're going to look at these polygons, these different shapes, and see if they are similar. And similar actually has a definition, not just that they're kind of alike, but for them to be similar, two polygons to be similar, they're going to have the exact same shape. They're going to look the same shape, but they'll be different sizes. There'll be a little one and a big one. So like two triangles that look the same, but one's bigger. That means they're similar. Now, officially to be similar, for that to actually happen, and here's a nice picture of, see, these are the same shape, but they're different sizes. But we're pretty picky about that shape. It's not just like in general it's a trapezoid, but it's got to truly have these two things. The angles within the polygon are going to be congruent. So you can see here that this right angle and that's a right angle. All their corresponding parts. So C here corresponds to I, and they have the same measurement for an angle. D corresponds to J, and they're going to have the same measurement. And then again, these right angles right here. The angles will have to be congruent. And then the sides have to be proportional, which means when you look at a ratio of this side to this side, that ratio has to hold true all the way through the figure. So you can see here, they've set it up, AB, that ratio needs to be the same as BC to HI. So if this is twice as long as this, then this better be twice as long as this. It's kind of like that all the way around the figure. If those two things hold true, you've got similar polygons. Now this was kind of a new look, that thing that was on that last slide. They call that an extended proportion. So a proportion is usually just one fraction equals another fraction. But if it continues to equal other fractions, we can just keep extending that proportion on down. Now the scale factor is that ratio of those sides. It says corresponding linear measurements, but that's the ratio of the sides, and that we're hoping that that scale factor stays standard all the way through. So looking at this example, it says find the scale factor of ABC to XYZ. All right, they've already shown that the angles, the corresponding angles are congruent, so we're good there. And now what we're going to do is we're going to do the extended ratio on the sides. And I'm going to say, all right, 15 corresponds to 6. So you can see this side corresponds to this side. And really they were really nice and oriented these triangles the same way. We really trust more than anything the letters down here. AB corresponds to XY. And then I'm going to say BC corresponds to YZ. So that's this 20 corresponds to 8. And then the last ratio there, AC would correspond to XZ. So 25 to 10. Now this is telling me to find the scale factor, so I'm assuming it must truly be similar polygons, because these ratios have to all be the same, and then whatever they are is the scale factor. They all reduce, so what we do is we try to reduce them. In this first fraction, 15/6, 3 goes into both, so I'll divide those out. And the next one, 4 goes into both. And in the last one, 5 goes into both. And you can see they all reduce down to this same fraction, and that right there is your scale factor, 5 to 2. All right, so now look, just talking generically without a figure here, it says DEFG is, and look at this notation right here, I think this is the first time this has popped up, is similar to HJKL. It's not congruent, there's not like the equal sign with the wavy line, it's just the wavy line. That wavy line means similar. All right, so what are the pairs of congruent angles? And again, trust the order of the letters. That has to hold true. That's why we're picky when we do congruent triangles, that we get the letters in the right order, because that means something. By looking at the order of the letters, I know that angle D has to be congruent to angle H, because they're both in the first position. And angle E would have to be congruent to angle J. They're both in the second position. And the third position, and I'm talking about up here, the first position, second position, third position, fourth position. So angle G is congruent to angle L. Those would be your congruent angles, how they would set up. And then part B says, what is the extended proportion for the ratio of the lengths of corresponding sides? So if I look at the first one, I'm going to go DE. Those are the first two. They have to correspond to the first two in the next one, HJ. And then I'd say that that ratio has to hold true all the way around the figure. So then I would go to the second and third. So that's EF would correspond to JK, which would be equal to, can you finish it? FG to KL, which equals, then I'm back to the last letter with the first letter, GD to LH. That would be the extended ratio for the sides of these polygons. All right, so if I look at these two, the question is, are they similar? All right, if they are similar, let's write the similarity statement, and we'll give the scale factor. All right, for them to be similar, I need all the corresponding angles to be congruent. So I have these two back-to-back right angles. I have that over here too. So this is not just, it didn't just shift over. You can see it kind of flipped over. So you got your right angles, then you got your single hash marks. These happen to have single, and then there's your double hash marks. So I do think all the corresponding angles are congruent. So that's the first thing you check. The second thing you check is if the sides are proportional. So when you look at the sides, when you compare this to its matching part, which I'm going to say is right here, that ratio has to hold true all the way around. So this 12 over 6 needs to hold true. So now let's look at AB. It corresponds to SR, so that'd be 18 over 9. And I sit there and I would do that all the way around the figure. Now in this particular figure I got lucky because they're the same numbers, 18 and 9, 18 and 9, 12 and 6. So they're all the same. I don't need to keep going with that, I guess. Let's check. Does this reduce to the same thing? That would reduce to 2 over 1. This would reduce to 2 over 1. And you probably could just do that in your head and you could have seen it in the picture. I'm just showing you if they aren't quite so obvious, here's what you would do. And then what's the scale factor? Let me do that again. We'd say it's a 2 to 1, or it's 2 times bigger, or 2 times smaller, whichever way you want to go with it. All right, and then the last thing they want us to do is write a similarity statement. We got the scale factor part, but you're just supposed to put these in the right order. So I'm going to go, in the first one, you just pick, I guess I'll start with A, and then B, C, D, E. You have to wrap around the figure, which works nicely there, is similar to, and you have to figure out what A would correspond to, and then what B would correspond to. So again, I'm looking at this as though it just flipped over like this line of reflection right here. It reflected and flipped over that. So if I had to guess, I'd say A corresponds to the S. So I'd put an S here. And then I'd say the B corresponds to the R. And then the next one is C corresponds to V. D corresponds to U. And then E corresponds to D. And that's my similarity statement right there. All right, so now it's your turn. I've given you 2 figures. You want to start off and check if all the corresponding angles are congruent. And then once you find that out, then you set up your ratio of all your sides and see if it holds true all the way through. If it does, then you'll know what the scale factor is and you can write your similarity statement. So at this time I want you to pause the video and go work on this problem. Come back when you're done. All right, so I do think the angles all match up beautifully there, and then I just started writing proportions. I'm looking at JK, comparing it to TU. All right, so that's a 12 to 6 ratio. All right, next I'm going to compare KL to UV. So that's 24 to 16. And then I'm going to go WV corresponds to ML. And I would keep going, but here's the thing. I noticed pretty quickly this reduces beautifully. 12, that's going to reduce to a 2 over 1. But this next one, that is not a 2 over 1. 8 would go into both. I could reduce it to a 3 over 2. That's not the same ratio. And I could keep on going and I get a different ratio on the next one. In general, I am not getting the same ratio and I'm supposed to. So I would have to say these are not similar. So then I don't write a similarity statement either, and I don't write a scale factor because it's not consistent. All right, let's make this a little bit fancier. I'm going to kind of put one trapezoid inside of another trapezoid. And you're going to compare. So you're looking at A, B, C, D, which is the big trapezoid. And you're comparing it to E, F, G, D. E, F, G, D. And so you have to find out kind of what it looks like it's oriented the same, just one got bigger. And so we know that they are similar because it says right here that they're similar. So the question is, what's the value of x? Well, that's a side length. And I can just, if I can figure out the scale factor of it, then I could go figure out what x is. The trick is to find a matching set from the two trapezoids that you know both measurements. For instance, I couldn't do it right on this leg because I don't know this leg. So that doesn't help me. That if I'm looking for x later on, yep, that's what I'm going to use. But it doesn't help me at this moment. I can't use the tops because I don't know this one. Let's look over here. Okay, I do know that this is 9 and this is 6. Okay, there we go. I have two matching numbers so I can see what my scale factor is. I just set up a little proportion. I'm going to say 9, which is the big one, to 6, which is the little one, is equal to, and I'm looking for the value of x, so I'm putting the big trapezoid over the little trapezoid. So the little trapezoid is x, and it corresponds to the 7.5. And now you're just going to do your cross products. This is what we did yesterday, cross products to see what this is going to equal. So 9 times x is 9x, and 6 times 7.5 is, I think that's 45. Let me check it. 6 times 7.5. Yep, equals 45. Divide by 9. X is equal to 5. Got it. Okay, now you see if you can use, you're going to use this same ratio here because that holds true through the whole set of trapezoids. Use that ratio to go find y. Pause the video, go do your work, come back. All right, here's what I got. Take a peek at it, see if you agree. If not, take a peek. I guess fix it so it matches mine. Okay, so last type of problem here, and this is kind of a fancy problem, so pay close attention. We're going to be using similarity on this poster design thing, which is, I kind of battle this sometimes when I'm working in a Word document. I'm trying to enlarge it or shrink it and make it all match up and be still proportional when I'm done. It says here that your class is making a rectangular poster for a rally. So you're going to make this poster. The poster design, which you probably put in Word or something, is 6 inches by 10 inches wide. All right, so you have this piece of paper or this design. It's 6 by 10 inches. The space that you want to put your big poster, the space that you have is 4 feet by 8 feet wide. What are the dimensions of the largest poster that will fit in the space? So I want to take my design, this 6 by 10 inch. I want to enlarge that design as big as I can make it, but I have to make sure that it still fits in the space allowed. Now this is not proportional. It's not like, oh, I just double everything and it fits. The shapes are not the same. A 6 by 10 is not the same shape as a 4 by 8. So we're only going to be able to enlarge it a certain amount before it starts to run over and get too big. So it says here, determine whether the height or width will fill that space first as you enlarge it. Well, the height is currently 4 feet. That's the space. I'm going to convert it so we have the same units. I took it times 12 to get it into inches. So I have 48 inches of height to work with. So take 48 divided by the 6 inches high that your design is. All right, and you're going to get an 8. Got it. Now we do the same thing with the width. The space I have is 8. The design I have is 10. So I first convert my 8 into 96 inches, taking it times 12, and then I'm going to take that space and I'm going to divide it by my sign, and I'm going to get 9.6. So now, the question is, which one will fill the space first? Okay, if you make your design 8 times bigger, the height is going to fill it up. If you can make it as big as the width here, this 9.6 times bigger, that's great. But what do you think happens as you make this width 9.6 times higher? If you do that, I shouldn't have circled that. If you make it that much bigger, then the height is going to start to get cut off, because it's not allowed to get that much bigger before it fills up the space. It only is allowed to get 8 times bigger. So you're always going to pick the smaller of the two numbers so that your poster doesn't get cut off. So we can go 8 times bigger. Pick the smaller one. Now, once you know that it can get 8 times bigger, well then let's make it 8 times bigger. We want to fill the space as best we can. So we're going to use the ratio that we know. So the 6 to 48, that's the ratio that we get to use. We're going to make it 8 times bigger. So this is my design. This is my space. This is my design. This is my space. So do your cross products. 6x equals 480. Divide by 6. X equals 80. Okay, so to keep this all nice and proportional as I enlarge it, I'm going to be able to make the width of it 80 inches. So that's going to be the largest well, actually, hang on. The largest poster, let's go ahead and put both dimensions. The largest poster is going to be a 48 by 80 inch poster. That's the largest poster. Okay, let's practice that one more time. It says, using the same poster design in problem 4, what are the dimensions of the largest complete poster that will fit the space? Recall that the design was a 6 by 10 inch design. All right, so I'm looking at which one am I going to fill up first. So I'm going to take my 3. Let's start with the 3 feet. First thing I'm going to do is take it times 12 to get it into inches, because the other value is in inches. And then I'm going to compare, all right, 6 over 36. Well, let's just do this. Let's just take the 36. And we're going to divide it by what we have for our design. So I'm going to divide it by 6. And that equals 6 times bigger. I could make that 6 times bigger. And I'd be okay for space. Now you're going to do the same thing with the other dimension. Right now it's 4 feet wide. Let's take that times 12 to see what that is in inches. That's 48 inches. Okay, got it. You have 48 inches of space. Let's divide that by 4. And you're going to get 12. So I can make it 12 times bigger. Well, that's great if I make it 12 times bigger. But if I make that 12 times bigger, part of the other dimension gets cut off, because it's only allowed to get 6 times bigger before it runs out of space. So remember, always pick the smaller one. I can make it 6 times bigger. So my my 6 inches that I have in my design gets to turn into 36 inches on the poster, which means my 10 inches on my design gets to be how big? Do your cross products. Okay, I get 60 inches. Okay, so what dimensions do I get to have for my for my poster. I know I have the space of 3 feet by 4 feet, but it doesn't enlarge to that perfect shape. So what I get to have then is the 36 that I had to make it 6 times bigger, 36 by 60 inches is how big the poster will end up being. It will fill up the width. It won't quite fill up the height. I probably said that backwards, sorry, just because of the dimensions. It's going to fill the height. It won't fill the width. All right. Hope this helps. I hope you took some good notes. Go work on your Math Excel. Good luck.